We are looking at a metal cube, and in order to determine its density, we need its volume and its mass. And since it's a regular shaped object, we could calculate the volume if we knew the length of each of its sides. Using a ruler, as you can see, we could determine each side would be 2.5 and the last decimal could be estimated 2.50 centimeters long. If we wanted greater accuracy, we would use a caliper. To determine the length in centimeters, we use the top graduation, and as you can see from the position of the 0, the cube is a little bit wider than 2.5 centimeters. To determine the next two decimals after the 2.5, we look at the top graduation and we identify which of the lines to the right of the 0 is perfectly matching one of the lines of the centimeter graduation below. The whole numbers on the top graduation are separated by 5 smaller lines, so every one of these small lines represents 0.2 of a whole number. And in this case, I would not be able to determine if the line of the 4 or the line beside it, the 4-2, align perfectly with the graduation lines of the centimeter scale below. So I would record the length with a number in between, and this would therefore be 2.541 centimeters in width. If you want to look this up, Google how to read a vernier caliper. To determine the mass, we could simply use a top loader balance, which would result in a mass of 43.0 grams. But for greater accuracy, we would use the more expensive, much more accurate analytical balance that would allow us to determine the mass to 4 decimals, to a tenth of a milligram. And that is so accurate that even the moisture of my hand and maybe some fat that I have on my skin would change the last decimal a bit if I wiped it off. Another way to determine the volume of an object, especially irregular shaped objects, is to displace the water in a graduated container. In this example, the beaker has graduation lines in increments of 10 milliliters. I would estimate the volume here is a bit less than 90 milliliters, so maybe 89 milliliters. To improve the accuracy, we could use a graduated cylinder. And in this case, if we look closely, the volume could be estimated to be 176.0 milliliters. And that means, two more significant figures, greater accuracy than with a beaker. In this lab, you will determine the density of what we call density bottles, small containers filled with lead pellets. And these little pellets are actually what kills the bald eagles when hunters do lose their game after they have shot it. And then the eagles eat that injured or dead game and get lead poisoning. We use the lead pellets to increase the density of these density bottles, which have, as you can see, a quite irregular shaped lid. We have added enough pellets to make these density bottles sink in pure water. But salt water has a greater density, so if we add salt to water, we can increase its density until these little density bottles start to float. And when that is the case, we can assume that they have the same density as the salt solution, and that is another alternative and quite accurate way to determine the density of an irregular shaped object, such as our density bottles. The density of salt water is directly proportional to its concentration expressed as mass percent. So to calculate the mass percent and then find out the density of that solution, we need to stay on top of the on top of the mass of salt we use for this experiment and the mass of the water used in this experiment. So start by pouring some salt into a 150 milliliter beaker and then weigh the beaker with the salt in it. Later on, when we have taken out some of the salt, we weigh it again and then we know from the difference how much salt has been used. The first mass to be recorded is beaker plus salt. We then take another empty beaker, weigh it, record its mass, then we fill it 3/4 full with water and weigh it again, record the third number, beaker plus water. The difference between the last and last but one weighing is the mass of water used in this experiment, and that mass will not change. We place the beaker with the water on a hot plate, but we will not use the heating function, we will just use the stirring function. We carefully drop the density bottle into that beaker and add a magnetic stir bar. After adjusting the stir bar rotation to establish a small vortex, you start adding the sodium chloride in small increments, always like a tip of a spatula full. Before you add any more, you always wait for all of the sodium chloride to dissolve. And sometimes that means to move the beaker on that stir plate so that the magnetic stir bar inside can disturb all the sodium chloride that you have added. At some point you will have added enough sodium chloride that the density of the solution is so close to the density of the bottle of the container you have in there that when you stop the stir bar, this density bottle will neither sink nor rise to the top of that solution and stay suspended for quite a while. Now you weigh the beaker with the salt and determine how much salt was used, and that allows you to calculate the mass percent concentration of your salt solution. We will provide you with a table of densities that correlate to the mass percent of the solution. Then it's cleanup time. You place all your containers in a sink and wipe down the stir plate with disinfectant wipe, and then wash your hands and leave the lab.